All right, so let's get started. And I want to remind you that every time you come to class, you should sign in, okay? So that you don't get deleted from the NTU Cool course site. So today I'm going to talk about the Zig-Zag lemma and the Mayer-Vietoris sequence in cohomology. So far, we have computed only a few cohomology vector spaces. We know how to compute the cohomology of the real line and an open interval, and that's about it. Okay, so in order to compute the cohomology of other manifolds, we need more techniques. And today I want to develop one technique called the Mayer-Vietoris sequence. Okay. And it's based on the Zig-Zag lemma. Okay. So last time we saw that an exact sequence of cochain complexes say 0 to A to B to C induces maps in cohomology. Actually, right now you don't need exactness. I mean, any cochain map will induce a map in cohomology. So you have HK of A to HK of B to HK of C. Right? And this is I star, and this is J star. Okay? So you have an induced sequence in cohomology for every K. Okay. Therefore, you have many horizontal rows. Now, what we're going to do is we're going to construct a linear map that connect together all these rows. So this linear map is going to go from HK of C to HK minus 1 of A, okay? And I will call it B star. In this way, you can connect together all the rows, and so you get just one long sequence. And the theorem is that if you start with a short exact sequence, then this long sequence will be exact. Okay? Okay. So the first thing to do is to construct this connecting homomorphism. Okay? D star. Okay. Okay. Now there are several steps. We start with the cohomology class here. Okay. So start with a cohomology class in HK of C. Well, since this C defines a cohomology class, that means C is closed. So DC is 0, okay? So D takes C to 0. Now, because each horizontal row of the original sequence is exact, okay? So that means J is surjective, right? So since J from BK to CK is onto so I'm gonna write it here. So you have BK mapping to CK, mapping to 0. And this is surjective. So there exists a B that maps to C. There exists a B in BK such that J of B, and to simplify the notation, I will often omit the parentheses, and I just write JB is equal to C, okay? So let's put the picture here. You've got this, okay? Okay, and then we have BK plus 1 mapping to BK. Right, to say that J is a cochain map means that you have this commutative diagram, okay? And so we have this commutative diagram. B maps to DB, and that should map to 0 under J. Oh, right, yeah. This should be CK plus 1. Thank you. Oh, I really appreciate this, because if you don't correct me, and this is filmed, the mistake will be there forever. Yeah. So whenever you see a mistake, you should point it out right away. I think I should give extra points to people who point out mistakes. Okay, that's step 1. Step 1 is you find that B, okay? And now, okay, now the thing is this. You see, you have an exact sequence here, right? And so because dB goes to 0, so dB is in the kernel of J, therefore it should be in the image of I. And so that means there's an A here that maps to dB, okay? That's step 2. Step 2 is you find that A. Okay, so we have a B now. Now, step 2. So since J of dB is D, just make J, look at that diagram. J of dB is D of JB. And that's D of C, and that's 0. By exactness, of the rows, there exists an A in A k plus 1 such that IA is dB. Okay? So I find this A. Okay? Now, is this A unique? Is there only one such A, or can there be many A's? So remember that each row of the original sequence is exact, right? So this is exact. Now I have an A that maps to dB. Can there be a different A that maps to dB? Okay, some of you are shaking your head. So tell me why. Yeah, because I is injective, that A is unique. There can only be one A that maps to dB, okay? You can't have two different A's that map to dB because then I would not be injective. So, so there is a unique A that maps to dB, okay? So note, A is unique because I is injective. Okay? Okay. So starting from C, now I have found something in A. Okay? That A should define a cohomology class. Okay? So what do you have to show? I have found an A. Does every A define a cohomology class? Yeah, it has to be closed. So that's what we have to show in step 3. Okay? So in step 2, we found the A, and then step 3, we want to show that A is closed. Okay? Yeah, so let me look at it here. Let me see. So we have A, okay, that maps to dB, okay? And we want to see what D of A is. Okay? So let's look at the commutative diagram. A maps to dB. D of dB is 0 because D squared is 0. And so dA maps to 0 by the commutativity of this diagram. And because I is injective, dA has to be 0. Okay? Yeah. So everything is really easy if you just look at the diagram. Okay? But we should write it out in words. So dA, IDA is DIA, okay? That's the commutativity of the diagram. But IA is dB, and DD is 0. And then since I is injective, DA is 0. So therefore, A defines a cohomology class. Therefore, the cohomology class of A is defined. Okay? So starting with a cohomology class C in HK of C, now I have found a cohomology class here. Okay? And that will be the definition of D star of the cohomology of C. Okay. Yeah. Okay, so that's a connecting homomorphism. Now, once you make a definition, well, you have to make sure that it's well defined. And in this construction, I have made some choices. Okay? So we really have to show that the construction is independent of the choices made. Okay? Now, can you tell me what choices I have made in this construction, in these 3 steps? Yeah. Yeah. What? No, what choices have I made? I can't hear you. Yeah.
Wait. Oh. The V.
B. Yeah, I made a choice of B because there could be many different B's that map to C. So I made one choice there. What's another choice that I have made? You know, once you have B, A is uniquely determined, so A is fine. But there is another choice that I made. C, yes, because we start with the cohomology class of C, but this cohomology class can be represented by different C's, okay? So I have made 2 choices. Yeah, in this construction, okay, this construction of D star depends on the choices of B, depends on choices of B and C. And to show that it's well defined, you know, you have to show that D star is independent of the choice of B and C. Okay. Now, I'm not gonna do that on the blackboard, okay? Because it takes up time and it is really quite straightforward. But you can see the details in the manifolds book. Manifolds, section 25. Okay. Okay, so now we have a long sequence in cohomology, and it turns out that it is exact, okay? Okay, now the thing that you really should remember about this construction is this picture really. But you don't need all the terms there. So let me just write down the essentials. Okay. So remember, the construction starts with a C, and we find a B that maps to it. Then we take BB, and then there's a unique A that maps to it, okay? So this is the picture that you should remember about the connecting homomorphism. And this is, well, what does it look like? This is called a zigzag in English. Okay? So we have this theorem that's called the Zig-Zag lemma. And the Zig-Zag lemma says a short exact sequence of co-chain complexes zero to A to B to C to zero induces a long exact sequence in cohomology. So the long exact sequence is what I wrote down before. We have this connecting homomorphism. Okay. And this is really useful for calculating cohomology, okay? Because when you have a long exact sequence, like if you have two zero terms surrounding another term, then you know that this one will be zero. So, that's how it works. And if you know that you have two zero terms, surrounding a pair, then this will be an isomorphism. Okay, so we'll do examples to show how it works. And the first example of this long exact sequence is the Mayer-Vietoris sequence. So the Mayer-Vietoris sequence is when you have two open sets that cover a manifold, and you can often compute the cohomology of the manifold from the cohomology of the open sets and their intersection, okay? Now, before that, I want to review a concept from manifolds or a partition of unity. Okay. So unity means one. Okay? And a partitional unity just means that you have functions that add up to one. You know, you partition one, okay? Now, the functions, well, there could be infinitely many of them, okay? So you need some restrictions so that you can sum them. Okay? And let me write down the definition of a C infinity partition of unity. A C infinity partition of unity on a C infinity manifold M is a collection rho alpha is some index set A of C infinity functions such that every point has a neighborhood on which this possibly infinite sum is actually a finite sum. And a neighborhood, for me, is always open, okay? Okay, so in this way, the infinite sum makes sense because at every point, it's actually a finite sum. Okay? And then of course, then the sum is equal to 1. Now, you can have, infinitely many functions so that locally it's a finite sum, right? Because, let me give you an example. So, for example, you might have open sets like this that cover the real line. And then you have, functions that look like this. So you have infinitely many functions. And on the real line, okay, they're all non-zero. But when you add them, you see that, every point has some open set on which only finitely many of them are 0, okay? So you can have infinitely many functions that's locally finite. And then if you start with an open cover, U alpha is an open cover of M. A partition of unity is said to be subordinate to the open cover if the support of rho alpha is in U alpha. Okay, so if for all alpha. Okay. So in this example, I can let the partition, let the open cover, be these open intervals. And then that's an example of a partition of unity that's subordinate to the open cover. And, there's a theorem from manifolds that given an open cover on a manifold, there is always a C infinity partition of unity subordinate to it. Right? Given an open cover U alpha of a C infinity manifold M, there exists a partition, a C infinity partition of unity rho alpha subordinate to U alpha. Well, I keep emphasizing that it's a C infinity partition of unity because in the holomorphic category, when you consider manifolds over complex numbers and you consider holomorphic functions, there are no holomorphic partitions of unity. Okay? So that makes the theory of complex manifolds very different from the theory of C infinity manifolds. However, in the continuous category, if you consider topological manifolds instead of C infinity manifolds, there is a continuous partition of unity. Okay? Yeah. So some theorems of topological manifolds, will also work for C infinity manifolds, but not for holomorphic manifolds or complex manifolds. And I'm not going to prove this theorem. It's a very technical theorem. But again, for the proof, you can find it in the manifolds book. It's one of the appendices. I think it's Appendix C. Okay. So that's all you need to know about partitions of unity. But maybe, I will give you an example of a partition of unity on the real line, subordinate to an open cover with two open sets. So let's see, what does the partition of unity subordinate to two open sets look like? Okay, so let's say that's the real line. And this is U. Okay. And then this is V. Okay. Okay, now, so you need two functions, rho U and rho V. Rho U has to be supported in U, okay? So it could look like this. Let's see. Rho U. No, it's one here. So this is rho U. Okay. Now rho V, if you have only two functions, rho V has to be just 1 minus rho U. So 1 minus rho U will look like this. It will be 0 here. And then, okay, they have to add up to 1. Okay, so rho V will have to look like this, okay? So that's what the C infinity partition of unity subordinate to UV looks like. Mhm. Okay, so now let's apply this to calculate cohomology groups. And we are going to get what's called the Mayer-Vietoris sequence. You know, the advantage of giving a Blackboard talk is that I have to move the blackboards, you know, I have to erase things and I have to write. It slows me down. And that's better for you. When I go to a talk that uses slides, you know, the speaker can just like, you know, move the slides, you know, and it's so fast, it's really hard to follow. Yeah. Yeah, so I always give Blackboard talks. Let's see, so yeah, now we're going to talk about the Mayer-Vietoris sequence. Okay. So let UV be an open cover of a C infinity manifold M. Okay, all the manifolds in this course will be C infinity manifolds. So I don't always write down C infinity. And we need a short exact sequence. So we will show that this sequence from M to UV to the intersection is sure exact. Okay, so let's call this map I and this J. And I is just a restriction. So I will take a form on M and it will restrict to a form on U and a form on V. This is what I mean by restriction. So a form, right, it's a function on the manifold, where to each point you assign an alternating K tensor. And you can just restrict the domain from M to U or to V. Okay? So I is just a restriction. Now J is, well, you first restrict to the intersection, but if you want this to be an exact sequence, then you need to subtract the two components. Okay? So J is a difference map. J of, let's say you have an omega on U and an omega on V. Okay, now there's no bar, so these are not restrictions of anything. Okay, it's just a form on U and a form on V. Is you take the form on V, you restrict it to the intersection, and then you subtract the form on U, restricted to the intersection. Okay, so J is the difference map. And obviously, if you take a form and you restrict it to U and V, they're going to be the same on the intersection. So when you take the difference, you'll get zero. So you can see quite easily that J composed with I is zero. Okay. And then, yeah, we have to check the exactness of this sequence. And exactness here is really easy, right? If you have a form that restricts to zero on U and restricts to zero on V, and U and V is an open cover, that form has to be zero at every point. So exactness here is easy. Exactness here is very easy to, I won't bother to show it, but exactness here is not so easy. Because what does exactness here mean? It means that J is surjective. And that means if you are given a form on the intersection, you have to write it as a difference of two forms. One on U, one on V. And let me show you why that's not so obvious. Okay, so let's just look at the K equal to 0 case. For K equal to 0, we have to show that given a C infinity function on the intersection, you have to be able to write it as the difference of two C infinity functions. So, for example, consider this function. Okay. here's the intersection, and let's say you have a function like this. You know, it's like secant, right? Secant looks like that. You know, this function, it blows up at this point and at this point. So how do you extend this so that it becomes a function on U? There's no obvious way to extend it, right? You can't extend it by 0. And that's where the partition of unity comes in, okay? So if you have a partition of unity subordinate to this open cover, say rho U looks like this. And you see that if you multiply your function f by rho U, it's gonna be infinite here. So it's not defined there, but because rho U is 0 here, when you multiply it, it will become 0 here, okay? So you can define, let me see. Yeah, so let me see, what is rho U F? So rho U F at the point P, on the intersection, you define it to be rho U P times F of P on the intersection, okay? And then you define it to be 0 on V minus the intersection. And why is it C infinity? Because, okay, on U intersection V, it's the product of two C and T functions, okay? So rho UF is C infinity on U intersection V as the product of two C infinity functions. Okay, now suppose you are at a point that is outside the intersection. So you are at some point here that's outside the intersection. Well, the thing is that the support is compact, okay? So, so P will be outside the support. So suppose now support of rho UF is contained in the support of rho U intersect the support of F. Oh, and it's in U intersection V. And it's the support is a closed set. Yeah. Yeah. So, but P, P is not in U intersection V. So P is not in the support. Well, if it's not in the support, then there's a neighborhood. W of P, okay, disjoint from the support of rho U F. And so on W, rho UF is identically 0. And so it's C infinity at P because it's C 0 in the neighborhood of P. So rho UF is C infinity on W, hence at P, okay? And that shows that rho UF is a C infinity function. And its support is actually inside V, okay? It's not defined over there. So and similarly, rho VF is a C infinity function on U, and you can write F as rho VF plus rho UF, because rho U and rho V add up to 1. But what we need is the difference of two functions. So you write this as, oh, just a minute. No, this is a function on U, right? So I need to write it this way. Rho UF plus rho VF. And then you write it as rho UF minus rho VF. And so this is a C infinity function on V. This is a C infinity function on U, okay? So that's how you write a C infinity function on the intersection as a difference of two C infinity functions, one on V and one on U. And that shows that J is surjective, okay? So thus, J is surjective. And I showed you only for functions, but for forms, it's the same formula. It's exactly the same idea. So this shows that, you know, J is surjective actually for all K. We showed it for K equal to 0, and it's the same for all K. Okay, all right. Okay, so let's take a break for 10 minutes, and you come back in 11:25. All right, sorry, I forgot my microphone just now. Yes, so I was saying that now from the short exact sequence, of co-chain complexes. Now we get a long exact sequence in cohomology, and it is called the Mayer-Vietoris sequence, okay? And so for the rest of the class today, we're just gonna do some examples using the Mayer-Vietoris sequence. You know, before that, there was actually like some other cohomology groups that we have to compute first. And I'm a little bit afraid that we'll run out of time. So I'm just gonna state this as easy theorems. So the cohomology of a disjoint union so if your manifold has two components, you know, say A and B, then a form on the manifold is just a form on A and a form on B, right? So it's just an order pair, and the differential acts independently. And so the theorem is that if M is the disjoint union of A and B, then the cohomology of M is the cohomology of A direct sum with the cohomology of B. Okay? And that's basically because a form on M is a pair of forms. Okay? That's one thing. And then another thing is homology in degree zero. So this is the theorem. If M has M connected components, then the zero cohomology of M, O, yeah. Well, in fact, right, we already know that, yeah, if you have M connected components, then the cohomology of M will be the direct sum of these K copies of cohomology, right? You can generalize this to M. Connected components. But in degrees, okay, but we don't know what the homology of each component is except in degree zero. So in degree zero, let's say we have just one component. So let's say if M is connected, so you have only one component. Then what's the cohomology in degree zero? Well, it's the closed forms over the exact forms. The exact forms are zero. So it's just going to be the closed forms. And the closed zero forms are the functions whose exterior derivative is zero. That means all partial derivatives are zero. When all partial derivatives are zero, what can you say about the function? Well, it's locally constant. Okay? Yeah. It would be constant on R, but like locally, you have coordinates, so locally constant. And a locally constant function on a connected set is constant. So, okay, I'm not writing down the details, but if M is connected, then H0 is R. And so if M has M connected components, then H0 of M is R to the M, M copies of R, all right? Okay, so we're just gonna assume these two theorems, and now let's try to calculate the cohomology of the circle. That's the simplest manifold after an interval. Okay. Here's a circle, and we need two open sets. So let's say this is one of them. U, that's an open arc. And this is another one, V. Okay. Now, the intersection will have two intervals, right? So this would be an intersection. This is part of the intersection, and so is this. So the intersection is the disjoint union of two intervals. Okay, now we know the cohomology of U. It's going to be the same as the cohomology of V because they are diffeomorphic to open intervals. Okay, so it's going to be R in degree 0 and 0 in degree greater than 0. Okay? But the cohomology of the intersection is the disjoint union of A and B, so the cohomology is going to be the direct sum of the cohomology of A and B. So it is going to be R plus R in degree 0 and 0 in degree 1. Okay? And now let's write down the Mayer-Vietoris sequence. Okay. So let's see, I'm going to write it this way. I have M, and then I restrict to U union V, and then restrict to the intersection and take the difference. The intersection is this joint union of A union B, okay? And we write down H1 and H0. Oh, M is just S1. H1 of S1, we don't know. H0 of S1, well, because S1 is connected, H0 is just R. And the Mayer-Vietoris sequence starts with 0. There are no forms of degree -1. And what is this? Tell me what to write down here. This would be H0 of U, direct sum with H0 of V. So what is it? Yes. Yeah, It's, oh, right, just a minute. Oh, you know what? U and V have intersection, right? But here, because what I want to write down is HK of U, direct sum HK of V. So I'm gonna separate U and V, okay? So that's why I write a disjoint union here. Because then when I take the cohomology of the disjoint union, I will get this direct sum, okay? So in degree 0, it should be R plus R. But that's a very good question, and I'm glad you asked. And then here, again, it's a disjoint union. So here it's R plus R. Okay, now this map is induced by I, so it's called I star. This map is called J star. So this is I star, J star, and then you have V star. And then in degree 1, you get 0 there, okay? So yeah, so we have to figure out what H1 of S1 is from this long exact sequence. This map is also I star. Okay, so so you see the H1 of S1 is the kernel of this I star in degree 1. Therefore, it's the image of D star by exactness. And the image of D star by the first isomorphism theorem is going to be the domain over the kernel. So R plus R over the kernel of D star. Okay, that's the first isomorphism theorem of linear algebra. And what is the kernel of D star? By exactness, is the image of J star. Okay, that's why you have to know what the maps are, okay? So this is represented by two real numbers, A and B, and J star is the difference, right? So it's B minus A. On each component, it's the difference. B minus A, B minus A, okay? So what is the image of J star? The image of this map. It goes from R2 to R2. The image is, yeah, it's a diagonal, right? Because these two numbers are the same. So the image of J star is the diagonal, which is one-dimensional, so it is R. Okay? It's the diagonal in R squared. And therefore, H1 of S1 is R, direct sum R, over the kernel of D star, which is R, direct sum R over R. So R2 over R is R. Okay? And that's H1. and H0, well, H0 is here, right? And in all other dimensions, it's 0. Okay, so we have computed the cohomology of the circle. Right? All right, in the homework, I ask you to compute some other cohomology groups, and you might need the homotopy axiom, which we will cover on Monday, not on Monday, on Tuesday. Okay, but in any case, yeah, you can read ahead and try to do the homework this weekend, or you can wait until next week. Yeah. All right, so we'll end here today.